Good morning, all. Good afternoon.
It could be afternoon. I always forget.
Could be.
Okay. We're on the East Coast. It's afternoon for you.
It is. All right. Okay. We are here at the 2024 Geo-Launchpad and RESESS Lightning Talks. I'm Kelsey Russo-Nixon. I'm leading this session with Anika Knight. Welcome. Thank you all for joining us. We do have some expected behavior here. Our code of conduct: please treat others with respect and consideration. As an organization, we value diversity in views and opinions. Be considerate, inclusive, respectful, and collaborative. Be kind to others, no personal attacks. Communicate openly with respect for others, critiquing ideas rather than the people themselves. Be mindful of your surroundings and your fellow participants. Respect the rules and policies of the meetings here today, and all communication should be appropriate for a professional audience. Please don't insult or put down others. We also like to acknowledge the land that we're on. As the ERSCO Consortium and the NSF Gage and Sage facilities, we respectfully acknowledge the generations of peoples and communities that have been and continue to be the stewards of the land we now use for our work. We ask to join us in acknowledging their communities, their elders, both past and present, as well as future generations. This acknowledgement is one small part of our commitment to dismantling the ongoing legacies of settler colonialism. We have QR codes down at the bottom of our notice stations that are on Indigenous territories, as well as more information on the historical territories of Indigenous nations. So we have two internship programs that we'll be presenting today. Half of them went yesterday, and we have another round of them today. So you'll hear from Geo-Launchpad students, and Geo-Launchpad is funded by the NSF GeoPaths project. It is specifically designed for community college students, and we reach students in Colorado, New Mexico, and Wyoming. And these are students who haven't had a chance to do research yet, or are really kind of just starting their journey and aren't sure where they'd like to see this, have an interest, but would like to see where this could go. And so this internship provides them an opportunity for the summer to gain skills, get them research ready, and also introduce geoscience career pathways. This project is also co-led with Front Range Community College.
And I lead the RESESS internship program. It's research experiences in solid earth sciences for students. It's a 1 to 2 year independent summer research internship program that focuses on earth sciences. The goal of the program is to provide authentic research experiences while also working on increasing diversity within geosciences.
And the two photos we have here are just them at in University of New Mexico at orientation week. So just some highlights from our programs. The programs really focus on career and scientific advancement of skills. And so we start that week with a group orientation week. And this year we did it at the University of New Mexico. Thank you for hosting us. We had a week-long orientation there, full of activities, including some fieldwork stuff that you can see here. We got to tour the ERSCO Primary Instrumentation Center down in Socorro. We did a lot of team building, a little bit of fun, and just lots of time spent together getting to know each other and being introduced to ERSCOP and geophysics. Throughout the summer, we host a scientific communication and writing workshop, as well as professional development workshops to work on soft skills. So we're really preparing students to create their posters and communicate their science effectively. Each week we go over a certain part of the poster and have the students submit drafts. And so we keep them going all throughout the year, working on that throughout the summer. Mentorship is a huge part of the program. And so not only are these students matched with a project mentor, but they meet with Anika and I as well. And then there's a lot of near-peer mentoring happens between both RESESS and Geo-Launchpad, just being at different levels in their academics. We host field trips when we can, and then all of our interns will be presenting at a conference this fall. So we have most of Geo-Launchpad at VSA and most of RESESS at AGU, some crossing over there, and maybe a few at a few other conferences as well. So if you're there, please come see us. So between the two programs, we had 22 interns, and they came from 22 unique institutions. We're really proud of that, to see just how far our programs are reaching, and the diversity of the students who are finding our programs, applying, and getting in. So here's a snippet of where everybody came from this summer. We could not make any of this happen without the National Science Foundation. RESESS and part of Geo-Launchpad are funded under our EarthScope Gauge grant number. And then RESESS has grown and has some REU funding as well from the previous IRIS REU internship and/or URIDES, if you're familiar with that one. And then, as I mentioned earlier, Geo-Launchpad is funded from the GeoPaths grant, and that's Front Range Community College, as well as EarthScope's grant numbers there. So thank you, NSF. We also could not do this without our amazing research mentors and project mentors. Thank you all. We really appreciate the time that you spent with our students. It's incredible how much they grow in a mere 11 weeks. And so we couldn't do that without you. Thank you so much. Thank you so much to our graduate assistant, Michaela, who helped students code and helped open or had open office hours, helped students when they needed it. She also gave us a great talk on what it's like to be a grad student, which is super helpful. And then additional thanks to Barbara Reynolds, who was a huge help in administrative support, all of the engagement team for their support, our FAD team, which is our finance, admin, and business team, IT, our compliance, and really just the entire EarthScope staff. Thank you, thank you, thank you. The interns this year worked at the following locations. So we had a pretty big cohort at New Mexico Tech, and we had a cohort at the University of Colorado Boulder. We had a few interns in Florida, a couple in Alaska, Sandia National Labs, University of Kansas, California Institute of Technology, as well as Penn State. So today we're going to hear from a mixed group of Geo-Launchpad and RESESS students. This is our agenda for today. And each student is giving a lightning talk, so that is 5 minutes. And so they've been practicing. They'll have some slides to show, and then we'll have a couple of minutes in between each person to answer any questions. So with that, we will get started. Oh, I got very dark there. Holly, feel free to share your screen. There it is. Okay, and Holly was
I'm muted, sorry.
Oh, you're good. Nope, Holly, I was just gonna say Holly was a RESESS intern, and please take it away.
All right, well, thank you. Hi, everyone. Thank you for coming today. I'm Holly McCrory Scott, and I'm a junior at CU Boulder. This summer, I worked at Florida International University with Shimon Widowinski and Marshall Higgins on coastal subsidence and its contribution to relative sea level rise in Puerto Rico. Sorry, my computer is very slow. I'm not sure why it's not changing the slides. There we go. Subsidence is vertical motion in the downward direction. It's also known as land sinking. And relative sea level rise is the height of the ocean relative to a particular location. As many of us know, sea level rise is a global problem that is a major contributor to coastal flooding. This project focused on Puerto Rico, which has many urbanized coastlines and communities that are vulnerable to storm surges and flooding hazards. Puerto Rico's government also places an emphasis on community resilience and finding bottom-up solutions to climate change and other hazards that threaten the local population. This project had 3 parts. We used GPS station data collected by the Nevada Geodetic Laboratory to create a vertical velocity map of Puerto Rico. We also used satellite data collected by NASA and the Alaska Satellite Facility to create an interferogram that shows subsidence during an earthquake swarm. and we used tide gauge data collected by NOAA to create a graph of relative sea level rise. The first part of the results of this study showed vertical velocity of 0.2 to 2.5 millimeters per year in the downward direction. The fastest rates of subsidence were on the western side of the island near Maguays. The second part of the results of this study showed subsidence of about 7 to 8 centimeters during an earthquake swarm that occurred off the southern coast of the island from December 2019 to January 2020. And the third part of this study showed 1.8 millimeters per year of sea level rise from 1962 to 1990, and 3 millimeters per year of sea level rise from 1990 to 2023. 3 millimeters per year is 1 foot of sea level rise in 100 years. This is consistent with global mean sea level rise for the same time frame. The main takeaway from this project is that land subsidence and relative sea level rise are contributing to coastal flooding in Puerto Rico. Future work of this project will include an interferometric time series to show subsidence over a much longer time frame. And this research and its future work may be used in coastal flooding hazard assessments. This work highlights the ever-increasing importance of finding bottom-up solutions to climate change to benefit vulnerable communities across the world. It is my personal goal to find these solutions to impact as many people as I can. Thank you. I can take questions if anybody has them. Sorry, Kelsey, I didn't mean to interrupt you.
No, you're good. I was just saying nice work, and I was gonna say the same thing. We're open to questions for Holly. Let's see. Christine Puskis from the chat says, do you have any comments on the tectonic setting?
I don't have a lot of information on that. I did not study too much about tectonics. I only know for sure that the interferometric work we did was related to that earthquake, the tectonic activity that happened during that time. If you want more information, I can direct you to Shimon. He would know more than me on that.
Great. And Moira says, Holly, great job. I remember you saying you got to make your own project. How were you able to narrow down what you wanted to actually study?
That's a good question. Thank you for asking. It was actually difficult. It was a little bit easier knowing that Shimon and his geodesy lab actually studied sea level rise and subsidence and some of those things. And so it was really easy for me to decide how I was going to use that. And really the biggest part of deciding what to do with this project was the location. And I ended up deciding Puerto Rico. And a big part was because of the vulnerable communities there. I have a personal interest in vulnerable communities, and it was there were a few that I decided to look at, but Puerto Rico was the easiest one to work with over the summer.
Yeah. Great work. And Holly, you've done other research internships before. Was this a totally new subject for you?
Oh my gosh, yes. I do not have a background in geophysics. I am just a geologist, and I don't have a huge background in physics or math or technology of any kind. I didn't use computers at all pretty much in high school, and this was really, really new and exciting for me because I got to learn how to code. I got to use some processing analysis processes, and that was really fun because I've never done anything like that. And I think I really expanded my skills over the summer doing that.
Awesome. You definitely did. Good work.
Thank you.
Thank you, Holly. All right. If anybody has any other questions, feel free to put them in the chat, but we're going to bring on Keiana. Keiana, please share your screen. Keiana was a RESESS intern also at Florida International University.
Everyone can see that?
Yep, perfect.
Okay, let me introduce you guys. It's hard to see with the Zoom.
I know, you gotta move everything around in all the boxes. It's okay.
All right. Good afternoon, everybody. My name is Keiana Mazzio. I'm a student at Fort Valley State University. I studied at Florida International University this summer to complete this project. This project is the automatic detection of creep using wrapped interferograms and its application to the Enrico Plantain Garden Fault. Some background on this project. It is located on the island of Hispaniola. It's in the southern peninsula of Haiti that we did the majority of this project. We focused on the 2021 magnitude 7 earthquake. It was a very strong earthquake that gave us a lot of data to work with, so it was a very good earthquake to choose. It was a strike slip fault called the EPGFZ, which is the Enrico Plantain Garden Fault Zone. We used data from the ASF Earth Data Bank to generate the interferograms that we used throughout the project. What you see to the right here is an interferogram that I created through different code lines in a Linux environment. And we were able to get a few of these for what you would call different paths and different swaths to have different imaging of the data. We were successfully able to create each interferogram that we attempted to create, and we were also able to read the data visually and numerically. We found that there was transient creep south of the fault line, and there was also another smaller section of creep north of that fault line. And these were really good finds because there have been research in the past that may have looked over that second area of creep or thought that it was moving and there were gaps. And we found that that wasn't quite the case. For our methods, we, as stated before, pulled our data from the ASF bank, and with the different code lines that we used in the Linux environment, we were able to create multiple interferograms. When we finally did create them, we were able to visually inspect them and see the creep and discontinuity with our own eyes, and have, scholarly talks about those things to understand the details and what we're seeing on the interferogram. And from there, we were able to map this red line right here. This is the EPGFZ. This is the fault line that we were following. This is where the earthquake happened. And these white lines are profile lines that we plotted 0.4 kilometers away from each other so that we could get an even reading of the earthquake across the continent from the east to the west. I'm sorry, from the west to the east. And the profile lines were created from south to north, so they're going upward instead of downward. As far as our results, we were able to successfully find visually the creep as stated before, and these graphs show profile lines from the last slide. This is profile line 8 going from west to east, and it showed discontinuity first at the 7 kilometers mark from the south to the north. And we were also able to find it in profile 10 around the, I would say, 7.5 kilometers upward. And we were also able to find it in 12 at two marks. We found it at the 6 kilometer mark, and we also found it again at the 12 kilometer mark. I mentioned earlier that we found a smaller area of creep that is the smaller area. So it was really cool to see that we were able to find creep on 2 areas of one profile line and not just one. In conclusion, we were able to detect visually the transient creep in the interferograms and profile lines. And we were also able to confirm our initial hypothesis that it is possible to manually and automatically detect the discontinuity. So even if it is a larger set, which we had originally anticipated, we are able to detect the creep in those. For my acknowledgements, I would like to say this is a work supported by the NSF Foundation under 2 different grants, and everything that we found is of our own work. But we have a huge thanks to give to NSF for the opportunity. And I also thank Florida International University for providing us the chance to work with Dr. Shimon and Michelle Higgins as well. And thank you to my home university for providing me the chance to find an opportunity as great as this one. And that concludes my presentation.
Well done, Keiana.
Thank you.
We can take questions.
Keiana, what was your favorite part of this project? I hope it was working next to me.
Yeah, you were a big part of making it enjoyable. It's fun to not be alone when you're in a new place. So that was a very big part of the internship. I also really enjoyed all of it. It was such a new topic for me, and geophysics is something I never got to dabble in, and it was a very good introduction. All the mentors were very hands-on. They taught me what I needed to know, and of course there were challenging days, but it was fun overall.
Awesome.
I
And
see Moira asked something. Yeah. I would say the most difficult part would be understanding interferograms. It took me a really long time because maybe you guys looked at the picture and saw, oh, there's a bunch of colors. I saw that too. And I didn't understand how to decipher what I was looking for at first, but now I'm able to, and I would say I'm very grateful for that. I see a hand raised.
Hi, Keiana. Thanks for your presentation. So I know Fort Valley doesn't have a geoscience major at it. So I'm wondering what you would take back to the other students at Fort Valley that you interact with. What messages would you have for them about your experience?
Well, thankfully, I can say we do have a minor program, which I am also part of. But I would definitely say that there are so many opportunities. A lot of careers and programs out there are very competitive and very hard to get into. And if you have a good specialty with science or with math or anything in the like field, you can take that over to geoscience where we need you and we will accept you. It's a very open and welcoming community. And I think everyone should at least think about joining it.
awesome. And then Christine has a question. Says, what follow-up would you like to do for the project?
Well, maybe you were able to tell that the project is not quite complete. It takes a lot longer than 2 months to automate something as big as that project is. So we definitely do want to continue following with that automatic process, which may take a while. But the aid that I have in my postdoc plans on furthering this project. Like I mentioned earlier, that second amount of creep was something that had been overlooked or misinterpreted in previous research papers. So he wants to continue that on and to go full depth and detail of what he now understands from the research I did this summer. And I think that's really cool. I kind of opened a project that they closed for more information that they can find and more things they can do with it. So I'm very grateful for that too.
Awesome. Great work.
Thank you.
Okay. Thank you, Keiana. Up next, we have Geo-Launchpad intern Jayce.
All right, let me just share this real quick. All right. Good morning, everyone. My name is Jayce Klein, and I'm a transfer student from Arapahoe Community College, transferring to the University of Colorado Boulder for physical geography. I'm here to present our research on surface velocity variations and bar formation in ephemeral waterways. Flash floods and arroyos leading into the Rio Grande are sudden, intense, and can cause significant damage. Understanding their velocity and bed load movement is crucial for improving prediction and mitigation strategies. They pose a serious threat to nearby communities, often leading to property damage and loss of life. And they can disrupt local ecosystems by altering sediment transport and deposition patterns and pose significant challenges for infrastructure. So accurate predictions are essential for designing structures that can withstand these extreme events. So our two objectives for this research were to quantify the velocity of flash floods in these arroyos and to analyze the movement of sediment and formation of bars during the flood events. For this study, we conducted field measurements during flash flood events in the Arroyo de los Pinos in central New Mexico. Can we pause for a second? My dogs.
Yeah, we don't hear if it's barking. That's okay.
Okay. Everything's fine. All right. We conducted field measurements during flash flood events in the Arroyo de los Pinos in central New Mexico. We primarily used a camera pointed at the channel and 3 reed-type slot samplers with pressure transducers and pressure pillows to measure the sediment levels during these flood events. We monitored several flash flood events over the course of a few years from 2021 to 2023 and captured the data on velocity and sediment movement. The footage captured during these events were uploaded to the program LSPIV. The footage was manipulated to obtain the velocity by cutting the footage into separate frames as still images, transforming the images to view the flow from above, and creating a 15 by 15 point vector grid across the channel, and allowing the software to calculate the velocity based on the foam and particles passing by as tracers. So after it was processed, the data was averaged across 3 channel sections as seen below and analyzed using statistical methods to identify patterns in flood behavior and sediment transport. Our key findings revealed distinct velocity patterns. We observed that the velocity of flash floods decreased when passing over formed bars of sediment. And this was evident both from our LSPIV results and the mean velocity measurements we gained. And the highest velocities were recorded over the Talweg, or the deepest part of the channel where the main current flows. Here is a chart depicting the mean velocities across different sections of the channel during a flood event on October 7th, 2022. And here is one on August 11th, 2022. And as you can see, the velocity is smaller in section 3 here, which indicates a bar has formed. And where the velocity is faster, that is where the channel is deepest. And this reflects in our mean velocities in the sections as well. Finding and further refining these results are important for several reasons. They enhance flood prediction models by providing detailed knowledge of how sediment formations and channel features affect flood velocities, and they inform the design of resilient architecture and infrastructure in these areas that need to withstand the varying flow conditions, especially in the critical areas like the Talweg. And lastly, they improve emergency response strategies by identifying areas with decreased velocity, helping to plan safer evacuation routes. With these floods, the waters are often very murky. So being able to tell where the water isn't as deep without being able to see it can be important when you need it most. And further research can help mitigate the detrimental effects of flash floods on both communities and ecosystems if we focus more on visualizing without having to see. This research was supported by the following grants from the National Science Foundation. And I'd also like to thank EarthScope for their tremendous support throughout all of this. And special thanks to New Mexico Tech's Earth and Environmental Science Department and the Bureau of Geology for providing us with guidance that we needed to succeed. And lastly, a big thank you to my research partner, Jonas Andersen, who helped me through a lot of the data analysis. And without him, I don't know how I would do this. And thank you for your time. And I'd like to answer any questions that you have.
Fantastic, Jayce. Patrick, go ahead.
I was just curious, first of all, great job. I was curious, how many flood events were there during that time period?
Wow, there were, I would say, around 20. My partner and I separated them between us, and we looked at certain floods to try and answer each of our questions. For mine, I used a lot of these shallow floods because it was easier to image the depth and the bar formation through those.
Okay, thank you.
Okay, and Moira asks, how did this project align with your interests/studies in geography?
So this was actually an amazing way to point me towards what I wanted to do with geography. So hydrology and fluvial geomorphology has always been kind of an interest for me, and being able to work firsthand with flash floods and arroyos really clarified what I wanted to do with my degree. So it was both a learning experience for what I wanted to do, and it helped clarify things for me. So I was really thankful to be able to work firsthand in these conditions.
Awesome. I'm curious, did you run into any challenges during the project?
Yes, the LSPIV program that we were using was a struggle to use, and it took us quite some time to get it up and running properly. But eventually we were able to push through and analyze what we needed.
Awesome. Great job. Okay, thank you again, Jayce. Great work. And such a nice lead in to your partner who worked similarly or alongside of you. So Jonas, also Geo-Launchpad intern, you can take it away when you're ready. Oh, you're muted.
Thank you. Hi, my name is Jonas. I also worked with Jayce on a similar project. So if you're like, hey, I think I've seen this before, they're very similar. But let me share my screen. Perfect. Then let me know if you can see that.
Not yet. There it is.
Okay. So my name is Jonas. I'm from Front Range Community College, and I'm a biochemistry student. So my project was on assessing the influence of sediment loads on the surface velocities of flash floods. So quick introduction. Basically, so our project is that we were analyzing a bunch of floods from 2022 to 2024 from the Arroyo de los Pinos, which is an ephemera of the Rio Grande. And basically, it's this site near New Mexico Tech. And it leads in. And then what we did is we used LSPIV on these flash flood videos that we had gotten to figure out the surface velocity. And then I personally, and then compared that to bed load flux data that we'd also gotten from those sediment traps. And then, so why is this important? Why would we want to understand this? Well, it's very important to understand for learning how erosional processes work and understanding flood safety. These are very important things. And also, like, flash floods are very dangerous, and we don't know about them as much as we could. So some of the methods that we used is as we talked about in the last one, LSPIV, which is large scale particle image velocitrometry. And I personally think it's very important to talk about it. Basically what it is you can see over here on the leftmost image is that you have you have your river or you have your, tributary, and you get a camera and you get these ground reference points. And what you do is you're able to use ore rectification to take the image and process it. And then what you use is, as you say, particle tracking, which is all those little dots. And then you're able to figure out, like, visually and remotely, like, how fast the river or, body of water is going, which is very interesting. So our measurement site, which is kind of, I got two pictures, the one on the bottom left and then the top right, which, so that was what we use as our reed slot samplers, which we use to collect the sediment and like bed load flux to compare. And then we also had a variety of other instruments and options, such as like the hydrophones and the stilling well, and that we used to also compare with. And then down here in the bottom right, we also used Fuda LSPIV, which was the software that we used to compile our data and kind of get these, velocities and like, the particle tracking with the arrows. But yeah. So we analyzed 5 different floods, and then we analyzed 4 different parts in each flood. We analyzed the beginning, the end, the middle, and then when the sediment traps were filled. So I also tried to analyze a variety of flash floods. We had a small flow flood, two medium-sized floods, about 12 centimeters, 20 centimeters. These are the peaks that each flood kind of got to at this point. And then we also had a night flood and then a very, very large flood at 86 centimeters, which was very high. But some things, and then over here on our top right, we have the kind of data tables we set up. So like earlier before, we separated into 3 different sections where we analyzed the velocity in each different section and then compared it to the bed load flux at the time. And we had some complications with like getting our videos, and also we had a problem with people who would keep walking into the river, and then that would mess up our data, which is kind of funny. But we found that it was also hard to do night floods if we didn't get enough light. It could also mess with the LSPIV, and we wouldn't get accurate velocity results. But so interpreting the results, this is still something I'm working on with my mentor that I've emailed. But there does definitely seems to be a clear positive correlation between flood surface velocity and sediment bed load flux. However, there also appears to be diminishing returns as the flood speed and depth increases. So this is definitely something that needs to be explored a little bit more, but it's very interesting. And then the acknowledgements. Yeah, that was my that's my presentation. And then also a big thank you to Jayce for also, helping, especially with figuring out the software. I really thought for a moment there we would have to learn French, which would have been terrible. But yeah, it's great.
Why French? The audience is wondering. We know, but
Okay. Yeah. So the software Fuda LSPIV was developed in France, and so when we initially downloaded the software, it was in French. So that was very annoying. But then he figured out how to change the language settings to get in English. So that really helped us not bumble around as much with the analysis. But yeah.
interesting.
Any questions?
Yeah, so Moira asked, I figured your least favorite thing was the coding in French, but what was your favorite thing?
Yeah, so we actually didn't have to do too much coding, which that was nice. But definitely my favorite thing is so when I was doing like my project, they had us go to like the actual site, like with the Rio de los Pinos, and we got to hang out with other grad students there, and it was really fun, like just waiting around because we're like, oh, are we gonna get a flash flood? Like is like water gonna come down the stream? And like like we'd play games and like like run around. Like it was just really fun, like meeting and talking with people, and then eventually getting to see the flood.
So you did get to see one?
Yes.
Cool. So were you guys just waiting in the rain?
Yeah, kind of. The one flood we actually did get to see, it didn't rain that hard. So that was kind of nice. But yeah, no, it was just really hot. I mean, that's New Mexico for you.
Christine asks, what kind of uncertainties did you find?
So especially like as I was mentioning before, especially like with the night floods, and then I think we talked about this a little bit in Jayce's presentation, but we found that like especially the amount of light really affected like how well LSPIV would work. And then there was also some because the channel would also change sometimes, like based on like the like I don't want to say power of the flood, but so like we'd also like like there'd be like small erosions, and then like also as I mentioned before, like people walking in the river. But yeah.
Awesome. Thank you, Jonas.
Yeah.
Okay, up next, we'll hear from RESESS intern August. When you're ready.
Hello, everyone. Hang on, let me just pull up my slides here. All right, can you guys see that?
Perfect.
Okay, so I'm August Puckett. I'm a student at NC State University in Raleigh, North Carolina. And this summer, I had the pleasure of working with Dr. Noelle Jackson and her amazing team at the University of Kansas. And we called this project Detecting Offshore Seismicity in Cascadia. So first, I mean, I'm in a Zoom call with a bunch of geoscientists, but so I'm sure many of you have heard of the Cascadia subduction zone, but I will recap it just a little bit. So Cascadia, which includes Oregon, is part of the only active subduction zone in the continental United States. And it has a propensity for these megathrust earthquakes, which are just no fun. Every 300 to 500 years, there's projected to be a magnitude 9 or greater earthquake, with the last one being in the year 1700, which was 300 years ago. And though Oregon's not the only state in Cascadia, if this magnitude 9 or greater were to occur, it's projected that that would cost us at least $50 billion in damages, and that's just in Oregon. So yeah, not good. To understand that a little bit better, I'm going to talk about slow slip or slow earthquakes. So when you think of a typical earthquake, there's a buildup of stress and tension, and then a release of it very quickly. But with these slow slip events, the tension builds up, but it's released over hours, days, even weeks. For a long time, we actually didn't even think there were earthquakes in Cascadia. Now we know they are. They just are a little different. If you look here on the right at figure 2.2, you can see all those red dots are places where we've seen these slow slip earthquakes happen. And so we care about that because these small earthquakes building up tension can add strain to the fault system and could potentially cause this next megathrust earthquake. So it's in our interest to find out more about this system as a whole, including the slow slip events. So working with Noelle, we use these sensors that you can see in 2.1, which were designed by Mark Zumberg at the University of San Diego. And they're called an optical fiber strain meter, or seafloor optical fiber strain meter. And these are the very new. We have not used these except here in America. And the way these work is you essentially take a long fiber optic cable, you stretch it out, you tension it, and you place it just a little bit under the seafloor. And by doing that, every time the Earth moves or there's some kind of tectonic event, the cable will stretch and contract, which is then measured by a computer, and it gives us not only like motion of the plate and how it's moving, so geodetic information, but also the seismic data. So this summer we looked at a little bit of that from the seismic data from October 2022. We got 11 months of data total, but right now we started off with October. So the top two figures you can see in 3.1 on the left, that is a magnitude 3 earthquake that we found with this sensor. And it's also confirmed in the USGS catalog. That was on October the 6th. But on the right, you can see a very similar event the day before, but that's not in any databases. And we found these by taking the time series data, and we used a computer algorithm to find earthquakes, as well as we went through by hand and looked over the whole time series and found those events. So what does that mean? Well, as we saw in 3.1 and 3.2, those figures from the last slide, we have earthquakes happening that we don't know about. But we actually found 35 earthquakes that we are very confident are actual events. And only 9 of them were in any kind of catalog anywhere. You can see that on the graph on the right. So what that means is it's possible that there are other areas where slow slip is happening just by the shore, as we saw. And we need to figure that out to have a better understanding of the system as a whole. So we're hoping in the future to use a few more strain meters and find more information. But yes, that's my presentation. Thank you for your time. I'd also like to acknowledge the NSF and RESESS for funding the project and also helping support us all. And I'll take any questions you guys have.
Nice work, August. Questions?
Okay.
Christine says, this technique looks like it has potential. What depth were the strain meters placed?
2 centimeters. Very shallow, basically right on the surface. They're just covered by a little bit of sand. But it has really high resolution for the local area where it's placed. Oh, depth underwater, do you mean?
Well, yeah, 2 different people. Shelley's maybe wondering depth underwater.
Yes, depth underwater.
Okay, yes.
Okay.
Okay.
I'm not entirely sure of the exact depth, but I do have the exact coordinates for the sensors, so I could get back to you on that. I do know that they're relatively shallow. They're only a few kilometers offshore. So I'd be happy to get in touch with you with that information, and I can get you in touch with Noel also.
Perfect.
Okay.
Moira says, August, amazing work. That is such cool results. What was the most rewarding part of this internship / research to you?
That's a great question. For me, definitely being able to contribute to this field of science, because this obviously this project could be very important in saving not only a lot of money and building up like better infrastructure and more resilient infrastructure, but also literally saving people's lives. And while obviously this is a small part of the overall project, it's really meaningful to me to be able to contribute to that and to help out the team under Noel Jackson.
Awesome. We got a couple more questions in the chat. And then Michael, I saw you raised your hand, but then you took it down. So I'm not sure if you still have a question, but Roland in the chat says, did you try to find those 26 new earthquakes in waveforms from nearby seismometers on land? Then you could possibly locate them.
Well, I think if I'm reading this correctly, you're saying we can cross-check them with the offshore seismometer here, and then also onshore ones, which we were doing to some degree. That's how we found the 9 earthquakes that were cataloged. But then there were also the remainder, the other 26, they were not, there was no seismometer that picked them up on land. So that means that must mean they're either really local events or something else that we haven't quite yet understood. I think am I answering your question?
Yes, you did. I was wondering if you looked at the waveform data. So they're definitely not in the catalog. That makes sense. But I'm wondering if you check the continuous waveform data, if there's still a little blip, right? Then you could use those additional seismometers.
Oh, I see. No, I have not done that. I'm not entirely sure if that has been part of the project. If it is, I'm not aware of it, but I'm sure Dr. Jackson would have more information on that.
Cool. Great
So I'd
job.
be happy to
Thank
get y'all
you.
in touch. Thank you. Thank you so much.
Okay, we've got 2 more questions. Christine says, what are the limitations on how long the equipment can be left in the field? For example, battery life, approximate water depth is okay.
So typically these go for about 11 months at a time. We actually had one of the batteries just spontaneously stop for this most recent year. It's now been on year 2. So now we only have one of the optical fiber cables running, but they typically last 11 months. So once a year, Noel and her team, they go out and physically using a robot called Jason from NOAA. They go down there and replace the battery and take the data up, and then we can analyze it. But yeah, about 11 months. And approximate water depth.
I think that might have been in reference to the first question that she asked, that you gave approximate. You were saying approximate water depth was okay. I think that's what she said.
Sure. Okay.
Yeah, that's correct. I should have said last question for that one.
Okay. Thanks, Christine. All right, and last question before we move on. Anyone else is welcome to continue their questions in the chat. But Shelley says, great presentation and project. This could really help us with scientific knowledge and preparedness for the next big one. If you have a map of where these were deployed, could you show that?
I do have a map. I don't have one on this computer.
That's okay.
I would be happy to get back to you with that, Shelley. If you'd like for me to email you that, I can definitely do that.
Okay, perfect.
Perfect.
Thank you, August.
Thank you, guys. Thank you for your time.
Up next, we have Geo-Launchpad intern Moira.
Okay, is that all good?
Perfect.
Okie dokie. Hello, my name is Moira. I'm a student at Red Rocks Community College in Lakewood, Colorado. The project I was working on this summer was investigating the interannual variability of stream flow in the Southeast US and its climate controls. And I was doing that under the guidance of my mentor, Enrico Zorzetto, out of New Mexico Institute of Mining and Technology. So a little bit of background. This research looks at how big atmospheric patterns like the North Atlantic subtropical high, or the NASH, which is like a big high pressure area over the North Atlantic Ocean. And I imagine it as a giant invisible balloon that pushes air downwards. And this high pressure means that air is not rising, so clouds and rain are less likely to form, and how that influences the flow of moisture, impacting rainfall and, as a result, stream flow, specifically in the southeastern US. And if you look at this figure right here, we are going to be focusing on this top yellow band over by the East Coast. So that's the subtropical high we are focused on for this project. And while many studies have looked at how climate indices affect rainfall, this one is unique because it focuses on stream flow, particularly focusing on summer stream flow and its relationship with atmospheric patterns like the position of the NASH. And then in turn, seeing if the NASH has any effect on extreme events, both very high and very low stream flow, i.e. flooding and droughts. And the goal is to get a better handle on predicting water availability and understanding how the risk of extremes changes over time. First, we looked at a data set showing where the NASH has been located in the southeastern US. We then created a map with points representing the different locations of the NASH and using those colors to show how the position has changed over the different years. We next took a list of all the USGS stream flow locations, plotted them also on a map, and then zoomed in to only focus on the sensors in the southeastern states. We then gathered data from these sensors, which included the flow rate of water for every single day since the 1980s. We then filtered this data to include only summer readings, since this is our period of interest in where we can expect a stronger appearance of the NASH. We then found the mean and maximum values of stream flow during the summer season for each sensor location. And then from that data, we calculated the probability or the return period of stream flow events, which was computed based on the intensity of each event at the sensor locations at a given year, which is like when you see on the news when there's a 100-year flood coming, it doesn't actually mean that there's a flood or a drought or whatever happening at exactly 100 years. But the closer that you get to the 100-year mark, the higher the probability is to have an extreme event each year. So in this figure on the right, it's saying that within a 30-year return period for where the stream flow is being censored, there's a likelihood that there's 10,000 cubic feet per second in a 30-year return period. Finally, we use this collected data to create a linear regression charts, which is a way to explain the relationship between a dependent variable, your y, and one or more explanatory variables, your x. This analysis helped us understand the relationship between stream flow rates, both average and maximum, and factors like latitude and longitude of the Nash, showing whether these geographic variables had any effect on stream flow. So the graph over on the left, it's saying that the further west you go, the less stream flow rate you're going to get. And so what have we learned so far from all this information? As frustrating as it is, but comes with science, is we have not learned anything so far. There might be some hints of correlation between the position of the Nash and stream flow rates, but the data we have isn't enough to confirm this. So what are the next steps? Well, we put all the coding we did for this single sensor in a loop, and then we'll be reading hundreds of sensors at once. And then we will put all that information on a plot to see if there are any similarities within those sensors. For example, when the Nash shifts, is there any effect on stream flow? And by analyzing this expanded data set, we hope to uncover more definitive patterns and relationships between the Nash's position and stream flow rates. And thank you to the NSF for funding. I really appreciate GLP, Geo-Launchpad, for giving me this opportunity to study over the summer. Thank you so much to my mentor, who met with me every single week over Zoom for hours on end to try and figure out coding. Thank you for Kelsey and Anika for every week putting on workshops, giving us training. I hope you guys understand how thankful I am for you. This has been a wonderful experience, and thank you so much.
Hooray, Moira. Fantastic work. I'd like to say that Moira was our only Geo-Launchpad intern who worked remotely as well. So different experience for her, but she killed it. Okay, questions? Okay, Louisa says, awesome job, Moira. What was your favorite part of the summer experience?
Gosh. So I really enjoyed orientation. That was really fun to get to meet all of you and to meet the team that I was working with and to see more on science that I'm not really familiar with. We did a lot of seismic studies, and that was really awesome. Not a job that I want, but it was really cool to see. But no, it was really awesome meeting everybody, becoming friends with everybody, connecting. Because I am a community college student, I met a lot of other students with a higher degree, higher education. So it was really interesting to hear their background and what they're coming from.
Awesome. Keiana says, great presentation. How could you relate this project to future works you're interested in?
I think a lot of the people that I've talked to over the summer know how why I chose this project. Is I'm super interested in water. I love water. I don't know if I want to do that with my life. So this was a cool opportunity for me to study these things that I think I'm interested in without paying for a college degree. And I loved it. I know this isn't your question, but the most frustrating and the most rewarding part was the coding. And I love coding. I am a weirdo, and it was so fun. So I'm definitely going to use that part of this project later on, is the coding. But I think I'm very interested in water still, so it didn't ruin what my thoughts and interests.
Awesome. Okay, 2 more questions. Holly says, great job, Moira. What was working remotely difficult for you?
Yes and no. I definitely missed the camaraderie of everybody, working together and having You know, the teams and people sharing a dorm room without AC, you know, like missing that stuff. But it was an awesome experience because I did get to work with my mentor like one-on-one every week. He made time and space for me with that, which I think was incredible. Also, I have my cats, so it was okay at the end of the day. But I've been pretty well with like time management, so none of that stuff really bothered me. It was more just like the field work part where it's like you guys are touching rocks and like I would like to do that, but I'm glad for the opportunity that I had.
Right. And Christine asks, what other factors did you have to account for to separate out effects of NASH, for example, El Nino, jet stream, etc.?
So that's something that we're still kind of working on. We did, with the stream flow rate, cut out the noise, where it was like we only took the readings that were like this, but not all the ones that are, you know, obviously not what we were looking for. But when we do narrow it down more, we're going to make sure more of that noise is canceled out. So that's, I hope that answered your question.
Thanks.
You're very welcome.
Great job, Moira.
Thank you.
Okay, and up next we have Summer. Summer was a recess intern. Or is still.
Hello. Share my screen. Right, it's still loading for me. Been having some technology troubles today, so let's hope that it works out.
I can see it, so I think we can see
Okay,
it.
that's good. I would like to be able to read it personally, but let's see if that happens.
Take your time.
Okay, there we go. Perfect. So hello, my name is Summer Czarnowski. I am currently an undergraduate student at North Dakota State University. I have one semester left. And this summer, I was so lucky to have an EarthScope internship and get to work at Sandia National Labs with my mentor, Elizabeth Silber. And our research this summer has focused on the analysis of early arrival of infrasound signals generated by bolide entries. So what is infrasound? Infrasound can be defined as low frequency acoustic waves. So these are all acoustic waves below 20 hertz. 20 hertz is below the range of human hearing. So we cannot perceive it auditorily at all. Infrasound can be generated by different events, such as explosions. These can be caused by either natural or artificial sources, such as bombs, heavy machinery, high altitude impacts. Volcanic eruptions and other forms of volcanic activity can also cause infrasound signals. Atmospheric entries, which is the primary focus of my work this summer. Which includes everything from natural objects such as bolides, meteors, to artificial objects such as space debris, re-entering space shuttles, hypersonic weapons, etc. It can also be generated by animals, which is kind of cool. Giraffes use it to communicate with each other, which I think is kind of neat. Though it is outside the range of human hearing, humans are said to have nausea caused by it, as well as feelings of anxiety. This is currently conjecture. Despite nobody being able to actually hear it, we do have ways of detecting infrasound. So currently there are 53 IMS stations in function around the world. These IMS stations are able to pick up infrasound that is generated by nearby events, dependent on how much energy that infrasound has, how strong the signal is, and how close the station is to the signal. So every infrasound event can be detected by none of these stations, or in theory, all 53 of them. But most often they're detected by around 1 to 5. And whether or not these detections happen is contingent on several different factors, such as how much station noise is present, how close the stations are to the event, what altitude the event happens at, all that sort of thing. So my work this summer focuses specifically on early arrivals. So early arrivals refer to the signal that is detected by the station from the infrasound event. So these signals travel through the atmosphere at varying speeds. The fastest it should be able to arrive is at the speed of sound through the troposphere. So on these two graphs here, you can see that as the red line. On the graph on the left, you can see the main part of the waveform is after that red line. That means that the main signal traveled slower than the speed of sound through the troposphere, meaning it arrived at basically the time that we predicted it was going to. However, early arrivals, which are present in many cases, arrive earlier than that red line. So you can see that on the right. The waveform appears a good bit before that tropospheric arrival, meaning there must have been some sort of outside influence affecting how fast that signal is traveling. So our work this summer focuses specifically on how these signals are arriving faster and what factors might be affecting that. So one thing we know about signals is that wind speed has a significant effect on them. In almost every case, wind propagation has an effect on whether or not the signal arrives on time, the strength that it arrives at, the back azimuth that it arrives at. So our first step is to take out that wind effect. We do that through wind propagation modeling, which consists of taking different intervals along the signal's path and calculating the amount of wind speed that is present at each atmospheric layer. And with that, we can get a pretty good idea of how fast that signal is traveling over the course of its path. Then if we take that out, we assume that the early arrivals are present even with that wind, and then conduct further analysis to determine possible causes of these. So this means we could be looking at multi-station detections. So this is determining whether events with, say, 20 station detections are more likely to be early arrivals than stations with only 1 or 2. This is also dealing with how close the range is for the signal to the event. Sorry, for the signal to the station. We're also looking at the light curves generated. So a light curve is a function of intensity over time. So we can look at the intensity over time generated by that atmospheric entry and see if there are any features that might be present between a lot of early arrivals. So if there's a peak at a certain point in its path, if there's no peak, if it's flat. So we're looking at that. Then we're also looking at the physical properties of bolides. So does velocity, entry angle, mass, do any of those have an effect on the speed? So that's been my work this summer. I've been so thankful to get this internship with EarthScope. I've really enjoyed it. I've loved working at Sandia and loved working with my group and my mentor. So it's been a great time. Thank you. Any questions?
Very interesting, Summer. Great job.
Thank you.
And we have time for questions. I have one. Oh, go ahead, Anika. I've been talking a lot.
What was it like working at a national lab? Do you think that's a career path that you'd like to go down? Because I know it's not something that's like super well talked about as terms of like what careers are like at a national lab and what you can do outside of academia.
Yeah, I really enjoyed it. The community here at Sandia is so nice. Like everyone is so supportive and they really like working here. I'm in this room with there's 8 other interns in here. Well, there's only 1 right now. But it's really fun to get to talk with them about my projects, about where we are, what we're working on. So I've really enjoyed it so far. And I'm working with Serena, another Sandia intern with EarthScope. And she's really cool too. We're roommates, so it's been a good time.
Awesome. Moira says, awesome job. Summer, what was the hardest thing for you during this internship?
I think this is a pretty common answer, but the programming. I had a lot to do with the propagation modeling, which was just a lot of going over the same thing over and over again, trying to get it to work. When it doesn't work, then I just have to try to do it in a completely different way. And I got most of it to work eventually, but one of the main issues is that a lot of our calculations take hours to run. So if you do something wrong, you're not going to know for another hour and a half. And then you got to go back and redo everything. But yeah, I think that was the hardest part.
And did you have any experience with this type of research before doing this project?
No, I haven't done any research, especially not infrasound research, prior to this, I had only heard of infrasound in terms of, you know, like paranormal activity shows, and they're like, oh, it's causing people to see ghosts or whatever. I didn't know that it was a real thing that people studied. So it's really cool to get to learn more about it and learn how like prevalent it is and how little studied it is. So
I loved the little tidbit about the giraffes.
I know, I thought it was so cool. That was amazing.
All right. Awesome. Awesome work, Summer.
Well, thank you.
Thank you. Okay. And we have RESESS intern Louisa Kaplan to take us home.
Hello. Come on a moment. I'll share my screen. Also sorry if you can hear my dog barking.
Can't. Zoom has done a really good job blocking out the background noises. I'm always like, can you hear my kid screaming right now?
Okay. Is that visible?
Yes.
Okay, awesome. All right, so my project this summer was on GPS analysis of spatiotemporal variability of deformation of the Slumgullion landslide. I'm Louisa, and I was working with Yankun and Roland, who are both at UC Berkeley. So we were looking at Slumgullion landslide, which is a large, slow-moving landslide in southwestern Colorado. It moves about 1 centimeter per day, and it's about 4 kilometers long, 150 to 450 meters wide, and 12 meters thick. And it's made of hydrothermally altered tertiary volcanic rock. So I was looking at spatial and temporal movement of 5 GPS stations that are placed on the landslide. And my data set covered August 25th to November 16th of 2022. And each of the GPS stations records its position every 15 seconds. So the first thing I looked at was just the overall movement of all 5 of the stations. So the top left map just shows where the GPS stations are placed on the landslide. You can see they're pretty grouped up towards the middle. And then north, center, and south are in a row in the middle, and upper is higher, and then lower is down below, and there's a reference station placed just off of the landslide. The top right figure is a visualization of what all of the stations did across all 3 months. So just from looking at this, it seems like upper moved more than the other stations, and lower moved a little bit less, and also lower seemed to move in a slightly different direction than the other stations, while south, center, and north moved pretty similarly, which makes sense because they're all in a row. The bottom left figure is another way to look at the downside movement of all of the stations. Again, it looks like upper moved more and lower moved a bit less, and then south moved more than center, which moved more than north. The bottom right figure is the detrended downside movement of all of the stations. So this figure is interesting because it does look like all the stations had a similar shape here. This is basically showing their deviation from a linear trend. So that could mean that there's something in the environment like rainfall or air pressure or something like that that's causing all of the stations to fluctuate in their movement in a similar way. The next thing I looked at was cycles of movement. So we have 3 directions for this: down the landslide, across the landslide, and normal to the landslide. There's only 1 station shown for each direction because they all looked pretty similar, but when looking at this, it does seem like there's peaks at 12 hours per cycle and 24 hours per cycle, which could mean that there's some kind of a daily cycle here, but also that bottom figure is a daily stack of one of the stations. So each of those colored lines is 1 day of data, and you can see those kind of diagonal lines going across it. Those are little bumps that are offset by 4 minutes a day, which could mean there's some kind of sidereal noise here as a feature of using satellite data. So the daily cycle that we see could actually just be a noise cycle from sidereal noise. Next, I looked at strain. So the left figure is a strain map. This is just showing the 5 stations, and then that circle is a reference station. So just from looking at this, as you can see, everything is in the negative, all the microstrains in the negative. So that means that this area of the landslide is pretty much contracting, which does fit with previous monitoring of this area. But the lower section is a light green, which means that it's close to 0. And we found that that was because the section is shortening in one direction and lengthening in another direction. So the overall change in its area is pretty small. That right figure is the velocities of each of the stations. So from looking at this, it does seem like the lower station is moving in a slightly different direction than the other ones. So both of these figures suggest that the lower section of the landslide is doing something slightly different than the rest of it, which is interesting. What do we do next? So first, as I mentioned before, sidereal noise filtering would be good to see if there's still evidence of a daily cycle after that noise is filtered out, and then look at correlation of displacement with environmental factors like rain, air temperature, things like that. Hopefully get a longer time period of data to see if there's a difference across seasons. Eventually down the line, figure out what these results suggest about physical mechanisms behind the movement of the landslide, and possibly do water chemistry of springs on the landslide because there are a lot of streams running across it. These are my references, and thank you to all these people at CU Boulder and to my fellow interns there. And thank you to NSF for sponsoring this program. I'd be happy to take any questions.
Great job, Louisa.
Thank you.
Okay, we have some questions in the chat. Moira says, really great presentation, Louisa. What was your favorite part of this summer experience?
I think I liked working with MATLAB because I hadn't done it at all. And I've used Python, so it was a good mix of like new things, but not like completely overwhelming. And I think it'll be useful. Also coding is very like love or hate, I guess. Like some moments I really hate it, and some moments I'm like, this is amazing. So that was fun because that was mostly what this project was, and just creating these figures was also fun to see like what's the best way to present this information was interesting to work on.
Awesome. Christine asks, do you have a profile of the landslide to show variations in slope?
In slope, I don't in this presentation. Oops, I can't go back. Oh, okay. Well, it's not in here because I didn't have it for it, but oh, here it is. This is just elevation. I don't know if that gives information that you're looking for, but it spans like 600 meters of elevation. In terms of slope, I believe the middle is steeper, but I'm not sure. I would have to reference something for that. There's nothing in this presentation that really explicitly says it.
Louisa, since you were in Colorado, did you get a chance to see the?
I did, yes. It was really cool. I wasn't sure I was gonna make it out there, but it's very strange looking. Like you can really tell that there's some kind of feature there because everything is like kind of yellow and like mushy, and the trees are growing at like weird angles, I guess because of the movement. I do have pictures. They'll be linked on my poster, but yeah, it was really cool. I went with Catherine, Ricky, and Roger from CU Boulder, so that was a really good experience.
Great. Okay, and Shelley says, great presentation and research topic. What future plans for this project or another project do you have?
Well, for this project, I'm not sure how much I personally will be able to do, but I think the sidereal noise filtering is probably something that I could start working on. It may or may not like be on my actual poster, but that would be like fairly simple to do and hopefully would help figure out if there's a daily cycle because that would be interesting to look at. And then also the correlation I could probably do. Unfortunately, I mean, I only have 3 months to work with just because that was like the longest continuous data that we got from the instruments. But those top 2 things I could probably start looking at for this project.
A question from Christine. GPS orbital period is 11 hours, 58 minutes. Did you use only GPS or other constellations?
I was looking at only GPS data.
I think in terms of other, Christine, you mean like GNSS?
Yeah, I was thinking like Galileo, Beidou, GLONASS. Depends on your equipment.
Got it.
Yeah.
Roland says, yeah, these are old receivers.
Okay, fair enough.
Okay. Great work, Louisa. Thank you.
Thank you.
Okay. And that wraps up today's presentations. Fantastic work. Thank you all for coming and supporting our programs and our students and engaging with them. They worked really hard this summer. We are so proud of them and so happy that they are able to share the work with the community. They all have LinkedIn profiles. At least that was one of their tasks this summer. So feel free to connect with them that way. And then please stop by and see us at GSA and or AGU if you'll be there. Thank you all. Everybody have a great weekend.